All right, thank you everyone for sticking around until the end of today. And of course, thank you to the organizers for putting together this wonderful conference and giving me the opportunity to talk. Let's see if I can talk fast enough to get us out on time. I'd like to describe today some work that I'm wrapping up with Jeff Jor, Stefan Yagori, and Nick Rod on the sensitivity of spin-precession axion experiments. So of course, this is going to be very much related to the NMR talks that we've been hearing over the past 2 days. And so is there a clicker with a, right here. There we go, okay. You have a laser? There we go, very good. Awesome. Okay, so I'll start off with a spoiler slide so that we can kind of see where I'm going to be headed at the end of this talk. So again, this is going to be related to NMR and, of course, the Casper experiments. So here I've reproduced the original plots from the Casper proposal papers from several years ago. So there are 2 samples that are used, xenon and helium. And so these are the projected sensitivities for nuclear magnetic resonance experiments. And what I'm going to argue today is that there should be some modification to these contours that looks as follows here. So yeah, dashed is the original ones. These solid ones are the ones I'm going to describe today. And so in particular, I want to draw your attention to the fact that what's important is that the slopes of these 2 contours are different for both xenon and helium. So that is what I'm going to be describing. And one of the key features to understand this is the idea of beats. Not these beats, actually mathematical/musical beats are what's going to be important. At least that's going to be half the story. So I'm going to dive right in then. So I'll set the stage. Of course, some of this will be reviewed from some of the NMR talks that we've already heard. So I'll consider an axion arising as a pseudo-Navier-Goldstone boson from spontaneous symmetry breaking at some high scale, or from dimensional reduction of a p-form in some kind of string theory compactification. I'll assume that this axion constitutes 100% of dark matter. And of course, the shift symmetry that this axion enjoys means that it's going to couple with either anomalous or derivative couplings to the standard model. So of course, the anomalous couplings are kind of the A-F dual sort of couplings that we describe when we're talking about the helioscopes and haloscopes for the photon coupling. And then the derivative couplings are what we look at for nuclear magnetic resonance experiments. So in particular, if axions couple to nuclei, then we'll have a term like this in our Lagrangian. Gn will be a coupling constant that is inversely proportional to the axion decay constant, and then there's some order 1 factor here in this CAN. Now, if we take the non-relativistic limit of this Lagrangian, then we'll get an interaction Hamiltonian that we've seen already, which involves the coupling of the nucleon spin to the gradient of the axion. And so if we compare that to things that we're quite familiar with in quantum mechanics, then we will see that the axion field acts as a pseudo-magnetic field, and so dark matter can be detected by nuclear magnetic resonance experiments. And so, as already has been described, this was proposed by Graham Rajendran, Budker, and Ledbetter from several years ago. But of course, we've also heard a bunch of great posters and talks in this conference using these sort of ideas in various contexts. And so I think I got just about everybody, but if I didn't, then you're implicitly included in the dots here. So I apologize for that. All right, so just as a very brief review, for more details, you can see the talk from yesterday about this, but the main idea for NMR experiments is that you've got some sample here in orange, you apply some uniform magnetic field, let's say in the z direction, and then instigate some uniform magnetization in your sample. Then, assuming axion dark matter exists, this will act like a pseudo-magnetic field that will introduce some orthogonal magnetization, which will then try and measure in a pickup loop. And so in particular, if you tune the Lamarr frequency by tuning the magnetic field, and you tune it to exactly the axion mass, or close enough, then you'll instigate some kind of resonance. And so that's the R in nuclear magnetic resonance here. And so what that means is that you'll get an orthogonal magnetization whose amplitude grows linearly in time. And so, of course, we've had a lot of discussion about this, the details of this setup, but what I'm going to be focusing on are the details of the actual magnetization itself here for the moment. So you can describe this magnetization by using that interaction Hamiltonian and then using the Schrödinger equation, but instead I will be using the Bloch equations, which I've written here. So the first term here, this m cross gamma b, this is what you would get from quantum mechanics. So this is magnetization, and then cross product of jar-magnetic ratio with the magnetic field. And then the next 2 terms are actually phenomenological in nature. So you've got 2 timescales here, T1 and T2. These are relaxation timescales that correspond to the system trying to return to that uniform magnetization in the z direction in our particular setup. And so when you try and apply this, the magnetic field that you're going to be putting in here is a combination of the uniform magnetic field plus the pseudo-magnetic field that is the gradient of the axion. Now, if you stare at this set of equations, you'll see that they're first-order coupled differential equations, but you can take a derivative and then uncouple them. And so that's what I'm doing here in the last line. But in particular, you also want to do a perturbative expansion in Gn, which of course is perfectly fine since this is quite small. And what you'll get is an equation that looks like this. So this is a differential equation. Here I've just written down the component in the x direction. On the left-hand side, you see that this is a very familiar friend. This is just a damped harmonic oscillator. And on the right-hand side, you've got driving terms that come from the Axion gradient. So, okay, that's very nice, but this is still quite involved. The left-hand side is very simple, but of course, on the right-hand side, you have to put in all the information about modeling dark matter and so on. So for the moment, let's just consider something very simple and replace this with just a simple cosine with some amplitude. And so now we'll go back to what we learned in kindergarten about how to solve this, this differential equation. And so we'll recall some characteristic solutions here. So let's take the limit that T2 goes to infinity. If we have the case where the driving frequency is exactly the natural frequency of the system, then of course we have resonance behavior. So this is the linearly growing amplitude that I described on the previous slide. But if we have a driving frequency that's only approximately equal to the natural frequency, then we'll get beat behavior. Then we can include a finite T2 here, and what the effect of the finite T2 is in regulating these solutions. So in particular, at low times, you'll still have this growing solution, but eventually that will taper off and reach a steady state solution for the resonance case. And very similarly for the beats is that you'll have some beat behavior, but then you get some solid state as well. And so these are the beats that I was describing at the very beginning. All right, so before continuing, I think it's worthwhile reviewing kind of the original argument from the Casper papers. So of course, the argument I presented on the previous slide is very simple, is that what you actually have to do is model the dark matter field not as just a single plane wave, but actually as one way to model the dark matter field anyway, is via sum of plane waves. And of course, this is related to some discussion Hendrik's talked from earlier today. Now, you only see this difference between the single plane wave and the sum of plane waves after you've run an experiment for longer than the coherence time. So the coherence time is something like 10 to the 6 over ma, roughly speaking. So before the coherence time, you basically see just a plane wave, but afterwards you start to probe the stochastic nature of the Axion field. Now, there was also a question earlier today about the scaling of sensitivity in the higher mass range, so I'm not going to go through the full derivation right now, but I'll just give the result and then kind of the assumptions that go into how you actually get this. So I'll focus at the moment for the high mass case. So what high masses means is that you have a lower coherence time, so we'll have a hierarchy where the coherence time is less than the actual experimental runtime, in which case then the sensitivity that you have, so the magnetization that you can probe, is something that goes like this in the original Casper papers is argued to be something like the square root of the noise, and then the coherence time times the integration time to the negative 1/4. Now then you can cast this into basically trying to get that slope in the Casper projections, and so that you would rewrite it as Gn is proportional to ma to the 5/4. And so this is exactly what that contour looks like in the Casper paper. Now, the two main assumptions going into this, for the first part here, it's the assumption number 2, the signal is in multiple bins. And so to answer kind of partially at least that question from earlier today, this is really the main thing that goes into deriving this negative 1/4 effect here. So the first assumption, though, is that the signal only grows until the coherence time. So this means that linearly growing amplitude, that only goes up until the coherence time. And then, as I said, the second assumption is that you're in multiple bins. And so the claim that I'm making here today is that both of these assumptions actually need to be revisited. However, this should be somewhat surprising because there's very good intuitive arguments for both of these. So for the first one, again, the point being that initially you can model the dark matter field as just being a single cosine. So then, as long as you tune your Larmor frequency appropriately, you expect to have resonance. But then after the coherence time, you don't expect to have the driving force to be so coherent. And so then you might not expect that you would actually have any kind of resonance behavior after that. So there's a good intuitive argument for assumption 1. And assumption 2 also makes sense because the idea being that if you're running your experiment for so long, so that the integration time is longer than the coherence time, that you should actually be probing the entire dark matter distribution. And so you'll have power in multiple bins. So there's good arguments for both of these, but I'll make other arguments as well here. So the first proposal is that I replace the statement that the signal grows until the coherence time with the statement that the signal grows linearly until the coherence time and then grows as the square root of the integration time until T2 on average. So there are at least a dozen ways that you can show this analytically, and I've done most of those, but I think that a plot is worth 1,000 equations, so I'll just give you this instead. So this is a result from simulations where on the vertical axis, in case you can't see it, is basically kind of the root mean square value of the magnetization. Then on the x-axis, I've got the time, and so you'll see two vertical lines, one corresponding to the coherence time for this set of simulations, one corresponding to T2, and then you'll have two other contours here. So there's one that's just a straight line with slope 1, and then one that's square root of time. And so the point here is that you can see that the magnetization grows linearly at low times, goes through a square root behavior at intermediate times, and then saturates at T2. which is exactly what this statement is saying right here. Now, the question is why? Because you gave very good intuitive arguments about why you would expect that perhaps the magnetization stops growing at the coherence time, and the answer is these beats that I described previously. Because what's going on is that when you're before the coherence time, you basically have a single plane wave, so you've got this growth. But what's actually happening, of course, is that if you use the plane wave approach to modeling dark matter, is that you have a bunch of plane waves that all have different frequencies. However, the dark matter distribution has the range of frequencies over the average frequency is something like 10 to the negative 6. So all of them are very close to the Larmor frequency when you're on resonance, and so all of them are really acting as beats. So what happens after you go after the coherence time is you're actually turning over some of these fields in the beat behavior. So you have the growth, but then they're starting to decrease as you're integrating along, but you have such a high number density of axions that you still have a bunch of axions that are still in the resonance behavior. So you can actually check that the ratio looks roughly like tau over t with how many you have that are still on resonance, and then you can use that to get this kind of rough approximation that you get like square root of t in the growth in this intermediate region. Now, for the second statement, it's actually more helpful to start actually trying to figure out how to derive results directly from NMR experiments. And for that, I'll take a DFT of the block equations. So here, I've got integration time, number of samples taken in time between samples. And I'll use this to define a power spectral density for the magnetization. And I get this. And so this is a rather long expression, but it's actually quite nice in a couple of different ways. In particular, it's got a factorized structure. And so the first term, or first factor, is the terrestrial factor, which involves aspects of the experiment, the magnetization, T2, and so on. And this is a Lorentzian with a width that's 1 over T2. And then the second factor is a cosmological factor that encodes information about the dark matter model. So this is really the PSD of the gradient of the axion. And so the statement then is that this PSD of the magnetization is what's actually sitting in one bin in basically both regimes, the high mass regime and the low mass regime. So low mass regime, again, means that you have a very long coherence time. And in this case, you expect that you're basically sitting in one bin because you can model the dark matter as basically being a single cosine, a single plane wave. So that makes sense. So here, blue would be the PSD of the gradient of the axion, and orange is this Lorentzian factor out in front. So here, you're just picking out a single frequency bin because of the cosmological factor. In the high mass regime, you have a low coherence time compared to the integration time, but the opposite happens. Yes, it is possible that it is true that you're going to be resolving the dark matter distribution, which here I've just shown in blue, but the point is that you're limited then by this Lorentzian factor out in front, and that basically makes you sit in one bin. So this is why you actually, even in the high mass regime, you are still sitting in one bin. And so, and so that's exactly the statement that I just made. And so you can analytically get to some results for this PSD. And again, this is using the plane wave model, where again, you have a Kronecker delta here in the frequency space, so you're sitting in one bin. Then you've got dependence on Gn squared, dark matter density, the magnetization, velocity, and the T2, and then the integration time T. Now, following the Casper procedure, we'll change T with mass. So in high masses, it'll just be equal to T2, so you basically run as long as you can while you're having a growing signal. And then in lower masses, you actually tie it to the coherence time. And so here I've got alpha as just kind of a factor that you can determine through numerical simulations, but just to get things to nice match well in the limit plot here. So of course, in order to actually derive constraints, sorry, not constraints, limits, you need to discuss the noise as well. So that has already been discussed in the previous two talks on NMR. So there is a squid noise, which I'll just take to be the exact value that they use in the Casper papers here. So in particular, I'm assuming that it's going to be frequency independent, just like what was done there. And then there's also a PSD for the spin projection noise, which has this following form that was discussed previously. There's also thermal noise, but we'll assume that the sample is cool sufficiently that we don't need to worry about it. And now you can take all of this, feed it into a likelihood framework, and then in particular, what I'll be using is the Asimov dataset to actually get an analytic way to get to 95% limits. And so if I do that, then I get this plot. So mostly this is the plot that I showed you at the beginning, but there's one other different feature, and that's these horizontal lines right here. So as I mentioned, the integration, the run strategy is that the integration time varies with mass at the lower masses, but then that means that the integration time is longer and longer for lower masses. So if you instead take a strategy where you just assume that you fix the integration time even for low masses, then this is like something you would get. So in this case, I just assume that I would say, okay, you integrate up until T2, just like for the high mass region, and you would get this instead. So this is the change to the limit plots that I propose, and there's a couple of comments that I'll make here at the end. So the effects that I described here with regards to the bins and then the beats is what gives you this enhanced sensitivity effect at the higher masses. And so this is really where the effects begin. Again, nothing I've described changes anything at the lower masses. It's only at the high masses right here. And again, it improves the sensitivity here. You lose a bit over, well, in this sort of intermediate region here. Now, this is applicable to any experiment utilizing NMR or related techniques. In particular, it is also true for Caspar electric. So in there, you don't have a gradient, but you still have the Axion field. And all of this beat thing is still true. The gradient actually doesn't really play any role there. It's all about the nature of the dark matter Axion field. And as a side note, I'll mention that if the spin projection noise can be mitigated, such as like what was discussed previously today about this squeezing technique, if you can do that, then actually the helium contour rapidly approaches the QCD Axion line here. So it doesn't quite touch it, but you can get very close, which is kind of an exciting proposal of trying to push this as far as you can to see if you can get to actually the QCD Axion line by using NMR techniques. All right, thank you.
We have a question from Arne.
First of all, super nice and interesting talk, even though it was extremely fast.
Oh.
But I mean, great stuff. I also, I mean, what are you doing next week?
Nothing in particular, I guess.
Because we have another workshop going on, and maybe it is nice to have you around if you fancy that.
Okay.
I just have one question. I mean, or maybe also a comment. We can also do it with protons. And then you have even higher gyromagnetic ratio and can explore further to the right. Your technique, how did it increase the maximum frequency?
So yeah, so that does not change. Nothing I described changes the maximum frequency. So the fact that there's a shift here in the x direction seems, as far as I can tell, purely from the fact that I use a factor of 2 for the Larmor frequency, and they don't in the original papers. And I argue that there should be that factor of 2. So depending on the definition of the Larmor frequency at the maximum magnetic field here that you have, that changes this shift a little bit. So this has nothing to do with the effects that I describe. That just apparently is some convention or some missing factor or something like this.
Well, it would be easier if you have a frequency axis on top. Anyway.
Yes, but I mean, I come from a different place of theory, so masses is better for me. But yes, yeah.
Yes.
Thanks for the great talk. I think actually the effect that you're describing comes from the fact that you're taking T2 of 100 seconds, which is fixed. Is that correct?
So the effect being like the beat behavior in all of this?
Yeah, because in reality, of course, it's not T2, it's T2 star that affects this. And that's never going to be longer than the Axion coherence time. Like the part per million is, I think, as good as it's going to get. So you're always going to be in the regime where the T2 star is shorter, at least in these proposals, is shorter than the Axion coherence time.
So the T2 star, if I'm understanding it you're correctly, this is the back reaction, kind of the include. So this is not 1 over T2 plus the other parts, or what are you describing as T star?
So that's exactly. I think that's the amount of time it tilts. You said the signal increases linearly. It only increases linearly for T2 star, then it saturates.
Yeah, right. Yeah, but that's doing the same thing as affecting as T2. I mean, at least physically, it's doing the same thing.
I'm saying you can't take T2 of 100 seconds. If you're at high frequency, your T2 has to scale with your frequency. And it will never be longer than the Axion coherence time, at least in these experiments as they are conceived right now.
Sure. I mean, so if that's a limitation, then indeed that would never happen. Indeed. So if you never go higher than the coherence time, then So this, and that's why it's only true in the high mass regime. So if you can go higher than the coherence time, but I mean, I would assume that you would want to try and do this at some. Oh, okay. Yes, that you would want to try and actually do this. At least this is the original proposal as well.
I think the Larmor frequency is G mu B or G mu times the magnetic field, and there is no factor of 2 that talk about.
It depends. I mean, so there's a factor of 2 in converting from the in doing the non-relativistic limit of the Lagrangian to the interaction Hamiltonian, and I think that's where the factor of 2 is that I have different. But I mean,
okay.
So indeed, yeah, that definition is unfixed, but I guess
but that frequency has nothing to do with Lagrangian. That frequency has to do with the magnetic field that you apply, right?
That's right. Yeah. So I'm trying to think of exactly where this is, but I mean, there is a factor of 2 what led to this, but it's been a while since I looked at it. But let me take a double check where it is. But it is a factor of 2 that I find different. Oops.
Last question.
Yeah, sorry. very quick one, I think. The Lorentzian that you were showing, I guess, for the when I'm trying to understand the different limits between whether you're, coherence time limited or T2 limited, I'm just trying to think. Isn't it also that the Rayleigh distribution should come here somewhere? I guess I'm just wondering, if you could give me some intuition for why why it's a Lorentzian that comes out of this for your signal, if that makes sense.
So let's just back up for 1 second. So when you say the Rayleigh distribution, are you which distribution are you?
Because I'm thinking that when you're thinking for something that's longer than a coherence length,
yeah, sure.
then the amplitude of your field is going to go as a Rayleigh distribution that you're sampling.
Yes. Okay,
and so
sure.
that's why I kind of thought that's what would pop
okay.
out.
Yeah, okay, so, well, I guess there's two things you have to worry about here. So everything that's related to kind of like what you're describing is hidden away inside the PSC of the gradient of the axion. So this I haven't described in any way. So all of that sort of stuff is hidden here. This part right here comes purely from basically the left-hand side of the block equations, because this is really kind of essentially kind of doing a Fourier transform of a driven harmonic, of a damped harmonic oscillator, and so that's exactly where this factor is coming from. So everything related to dark matter is hidden away in here, and this is purely from the fact that we're basically processing dark matter into an NMR experiment.
Okay, thanks.